we all live in a digital age at this point, and
can you hear the sound?
Yep.
Yeah, you heard it? Okay, that's terrific, because I'm going to have to mute my mic. There's work being done in the house. And everybody can see it, I guess. If you can hear it, you can probably see it. Okay.
and the difference between analog signals and digital signals are shown on this simple diagram. If I have an analog signal, normally I have continuous floating point values as a function of position or independent variables, say x in space. And so this is a height or a wave as a function of x. I can make that signal digital by sampling that function at discrete points as a function of x and just recording the values. And so my signal now is not an infinite set of floating point numbers. It's a finite set of discrete values, which are samples of that signal. And this is used in digital audio recording and in digital images for your camera. Brightness as a function of position in the camera is given as a number, height or brightness, a waveform of a sound wave instead of a continuous signal is given as a set of integer values. And when you want to transmit that information, it's very convenient because all you have to do is transmit these values and then reconstruct the signal from the transmitted values. Imaging, medical imaging, operates in the digital world, and this image is 512 by 512 point estimates of brightness, or pixels, and as a function of position, this is a human chest. This is the front of the patient, or the anterior side. Then their chest wall is the heart, and the spine is down here. If we zoom in more closely, we can see that under certain settings for how this image is displayed, you can start to see the discrete nature of the sampling of the brightness. In this case, this is a CT scan, so the brightness corresponds to the amount of X-ray attenuation at that point in the sample. If we zoom in further to this detail here, you can see that there is the discreteness is quite visible at this point. This way of displaying the image shows basically an artifact. The object is not composed of discrete sharp-edged boxes. This is just the way we're displaying those pixel values, but the spacing between the boxes gives you an idea of the sampling rate in samples per millimeter for the spatial resolution of that image. Really, we shouldn't display the image with these little boxes visible, because there's no point in doing that. You should just interpolate and display the image like this. We have many more pixels underlying the object that you're visualizing, and you don't see those crazy little squares. If we go back and look and plot through the discrete square values, and you can see as I'm plotting through this feature here, which is actually a little piece of calcium in a coronary artery, we have the discrete steps in its brightness as we pass through that. Those values themselves can be used just to create a smooth function that is probably a better illustration of what is in the underlying tissue. Sampling in 2 dimensions, as we just saw here, we characterize this mathematically with a sampling rate, or basically a sampling period. And so if I'm sampling in the x direction at a specific rate or period, delta x, I can visualize it like this, delta y, visualize it like this. You can see we're dramatically undersampled if all we took from this sample were these points. We change our sampling rate by changing this value of delta x, which is the separation between the sample points, the sampling cone. So if we're given a 2D continuous signal. So this is a function f of x, which is, a continuous function. What we want to do is generate a set of numbers, right? These are just discrete numbers that are indexed by m and m, such that when we look at that set of numbers, the relationship between those numbers and the function is the following, where this is the sampling period and m index which, how many steps across the function we're taking, and n is how many steps down vertically we're taking. And so we've replaced our continuous function f of xy with these discrete samples of that function. So these are called the sampling periods, and 1 over the sampling period gives you the sampling frequency or sampling rate. And for temporal signals like music, the sampling period is in milliseconds or microseconds, and the sampling rate is simply frequencies like kilohertz or megahertz. For us, when we're looking at images, the sampling period is in millimeters and the sampling rate is in cycles per millimeter. So it's basically describing how many cycles of a sine wave do you have per millimeter is the sampling rate. Sampling rates show up immediately in simple descriptions of CT scanning, because we're going to have an X-ray source that we raster across the patient who is sitting here, and then there'll be a detector that measures the intensity of X-rays that get through our object. And the separation of these detectors just in millimeters is basically 1 over that separation is the sampling rate across here. And as the geometry of the detector changes, the details of that sampling rate might change, but the basic principle is that there's a separation between this sample here and this sample here. And usually that separation in a modern scanner is about 1 millimeter on the detector, on that order. So you just count across the number of detectors, and that's how many millimeters are in your field of view. So in CT scanning, we have an X-ray source. It comes out of a small orifice and produces a fan beam of X-rays, and then here's our sampling grid. And so our sampling rate is going to be defined by how many sample points we have on that grid. This is what the sampling grid looks like, or the detector, the X-ray detector itself. It comes in component parts, but this is the theta direction, or if the patient was lying here, this would be the right-left direction. And this is the Z direction, or the direction from their head to their feet. And inside each one of these modules, we have a set of these little chips that have individual detectors on them, and they detect an X-ray, cause a flash, goes to a photodiode, which makes a voltage coming out, and that set of signals comes out of each one of these replicated chips. You can see it's plugged in here. This is where the electronic voltages come out. Here's the detector element itself. It's 16 detector elements this way, 32 this way, and they are separated by about 1 millimeter. Question: why can't you just make this thing 64 by 32? Just put 32 here and 64 along here to make a higher resolution picture, just as they seem to be doing endlessly with cell phone cameras. Now we're up to 12 megabyte or megapixel cell phone cameras, which is a 3000 by 4000 array. Well, you can do that. You can just make more cells. However, the efficiency of that detector may go down because there's space between each detector element. And also, you have to get a critical number of photons inside each detector element when you're measuring your signal in order to get good statistics. And so you just might run out of photons. So there's going to be a balance between the photon flux you think you're going to use and the dimension of these detectors. 256 detector elements this way, 832 this way when we're all said and done. So here's a continuous function as a function of an independent variable x, which is position in space, given in millimeters. And these are, let's say, X-ray intensities as a function of position in millimeters. In MR, this, if we're talking about sampling, this will be a function in time. We'll have a voltage as a function of time, and you'll measure those, you'll sample those voltages with an A to D converter. We want to turn this continuous signal, in our case for CT, it's an image that exists in space of X-rays that are flying through space with different intensities. And we want to essentially convert it to these discrete samples. Okay, so our continuous function sampled at n points, you know, at an nth point of delta x gives us a sequence of values as opposed to a continuous function. So we have a big question. How many samples do we have to take? Like, how finely do we have to sample this thing in order to have a high fidelity system, right? You can imagine if I sample very infrequently, I'm not really going to be able to tell you what this function is. So a more technical way of asking this question is, can we reconstruct the original continuous signal or the original continuous image from its discrete samples? So given just this sequence of numbers, this list of numbers, can I give you back this function? That's one way of asking that question. And then what are the consequences if you don't sample it well enough? If we undersample, does it cause artifacts, and what do they look like?
So the example we will look at initially is a time domain sampling. And if we have this signal, which is, say, a voltage measured as a function of time, which is what we would measure in our receiver coil in an MRI experiment. And we look at the time base. This is 100 milliseconds here, zeros here, and then we start oscillating voltage. We're going to sample that voltage that is a function of time at some rate, capital Fs. And what we'll do is we'll take the Fourier transform, the 1D Fourier transform of this signal, time domain signal, to look at the amplitudes of the sines and cosines that are required to construct this signal from those sinusoids. So when we look at those amplitudes, that's what the Fourier transform gives us. We plot that normally as either an amplitude spectrum or a power spectrum. The power spectrum is just the amplitude of those coefficients squared. And so this is in time, this is in hertz or cycles per second, right? So if I look at an interval, say, from 0 to 100 milliseconds, and I have 100 full cycles in there, that's 1 cycle per millisecond, so that's 1 kilohertz is the frequency component. So I come to my Fourier spectrum and I say, okay, here's a kilohertz here, 1 kilohertz, and that would be the peak at that frequency. You can see also that when we'll see this when we plot Fourier transforms of images, we often plot the relative intensity of a power spectrum or an amplitude spectrum as a logarithm because of the huge dynamic range of these values. And so here our dynamic range is somewhere around 1, and then as we go out to higher and higher frequencies, we get down to, you know, very small values, 10 to the minus 6 and below. So it's like 1/1,000,000th of the amplitude here. Not to say that down at 10 to the minus 6, 10 to the minus 5, there's still important information out here often. But sometimes it can just turn into noise, right? The point of this is, here's our continuous signal sampled at Fs. If we take every 8th point of this signal, we undersample, we sample more slowly, then the function looks like this. The sampled function looks like this. When we take its Fourier transform, the digital Fourier transform, the power spectrum looks like this. And that's quite different, obviously, than this. You can see that at around 0 in the low frequencies, you know, if you looked compared peak to peak, they're reasonably similar. But then as we get to higher frequencies, basically something very strange happens in that the whole thing just repeats itself over and over. And so out to about 3 kilohertz, we have this symmetric looking function around some center, and then the whole thing just repeats itself. And this is, you know, what happens when you're undersampled, is that information that's out at higher frequency wraps back into the lower frequencies, and you can only plot a finite bandwidth. And this bandwidth is entirely determined by the rate at which you're sampling this, or the delta t of your samples over here. A visual way to look at that is if I have a sinusoid of this frequency, say this is x space in millimeters, and I sample that oscillating function as a function of position. Obviously, this top one is well sampled. You know, I can see the phase and the amplitude of the sinusoid quite well. If I drop, you know, that sampling by a factor of 20 or so, such that I get these samples, well, the function that I'm looking at now is a much lower frequency sinusoid. See, I don't have the ability to resolve this frequency at this sampling rate. So the amplitude at this frequency appears or folds back into this lower amplitude here. So here's an example of sampling rate and aliasing. It's called the Wagon Wheel effect. And we'll play a video on YouTube to take a look at this. This is a really interesting video. I kind of like this thing. Let's go out here and hope that it plays back well. Sorry about the music. Don't need that. So here you can see, as the camera is sampling pictures of the positions of this, you know, object, you can see some of those rings are rotating clockwise, some are rotating counterclockwise, and some are stationary. And this is determined by the speed of the rotation of the ring and the sampling rate of the camera. If we went into slow motion, we would see something like this. We would see everybody rotating at the same rate. But when we're looking at it, whoop, too bad. He'll come back. But when we're looking at it at, say, 20 frames a second, we see multiple different frequencies of rotation of these patterns. You can see some are clockwise and some are counterclockwise. And it's interesting to see where they stop. Looks like it's constant. And then this is in slow motion. You can resolve, because the sampling rate is higher, you can resolve the actual frequency of oscillation of those different patterns. Okay, we'll go back to our slideshow here. So in medical imaging, here's an example of aliasing. If we have a film image, say of a chest x-ray, and I want to archive that in my picture archiving system, as opposed to my filing system, I need to digitize it. And so a lot of scanners were developed where you just digitize this picture that's on the left here. After that digitization, if the scanner's a cheap one and it doesn't digitize at a high enough rate, you get artifacts in the resulting image, which are these high frequencies, which are the aliasing of the high frequency information in this picture back into the lower frequencies that can be sampled with this digitizer. So one way to avoid these artifacts is to take this image, filter it such that the high frequency information is missing, and then digitize that, and you wind up with a clean image. It doesn't have this aliasing artifact, but it is a lower resolution picture. It's blurrier than the original. Here's another example of an aliasing artifact in an image where we have two different cameras being tested, and the fabric of this coat has a high frequency pattern due to the stitching. And this camera, you do not see that pattern. In this camera, the CCD image detector, the array of detector elements, is sampling at such a frequency combined with the optics such that you get aliasing of this low spatial frequency pattern on top of your image. And this is in fact aliasing of the power or the energy of the high frequency of the pattern back into the lower frequencies that are displayed, and you get this artifact. It's called a moire pattern, and it's an example of aliasing.
So we're going to look at this mathematically and develop a couple of functions to help us do so. Recall that the comb function is a set of delta functions arrayed on the x-axis in one dimension, so it's a continuous functions of a continuous variable x. If it's just comb x, then we have delta functions at the integer values 1, 2, 3, 4, and -1, or 0, -1, 2, 3, 4, etc. And that can be written down quite simply as a sum of delta functions whose peak is shifted by an integer number. It can be written down in two dimensions in a very similar way. And then we can derive a function called the sampling function, which is close relative to the delta function, just by scaling where the non-zero values of the delta function fall. And so here I have the delta functions are sitting on the integers in the xy plane. In this case, I can have the delta function setting on a continuous grid with a separation of m delta x and delta y. So every delta x, say every 0.1 centimeters, and every 0.1 centimeters I can have a sample spike, and I'll just count them out with these integers m and n. The relation to the comb function of this sampling function is just this equation here, just by looking at the analytical form of the comb function. A 1D version of the comb function looks like this. Again, it's just delta functions sitting on the axis separated by delta x. And we're going to use this 1D comb function to generate an analytical function which we call the sampled version of f of x. And that's shown here, where basically the weights or the heights of these delta functions are provided by the values of f of x at the discrete points that are separated by delta x. Now, to this point, this is our sampling function, which is it's a continuous function in x. So it is not itself a sequence or a list of finite list of values for digitizing our function. It's defined everywhere. And the definition is the continuous function times the comb function. Here's the continuous function times that comb function written out as delta functions. And you can bring this inside, since it's not dependent on n. And what the delta function does is it sifts out the value of f of x here at these discrete points. So now this is our list. This is our discrete representation of the function f of x, because this is just a finite list of numbers, or it's actually infinite, but it's sort of a countable list of numbers. We can do the same thing. We can define the sample function in the plane And what we get is a two-dimensional list indexed by M&M of these values of fxy at the points defined by the separation m delta xy and delta y. So we're going to need, in a moment, the Fourier transform of the comb function. So we'll just pause for a second and look at that. And recall that the Fourier transform of the comb function, or a set of delta functions, is itself another set of delta functions in Fourier space. So this is in space in millimeters, this is in cycles per millimeter. And so we get a separation of delta functions in Fourier space. And if we look at what happens when we scale the comb function so that we can put our points at arbitrary points n delta x along the x-axis, and so this is the new comb function. The Fourier transform of that, using the properties of the Fourier transform, particularly scaling property on the dependent variables, we get a comb function in k-space that is separated at intervals of 1 over delta x. That's the Fourier transform of the comb function that is separated at delta x. We get a comb function where the peaks are separated at 1 over delta x. So this is what it looks like graphically. Here's our comb function, set of delta functions. There's a separation between the points. Let's call this 1 millimeter, say. And then this is the separation of the peaks in the Fourier transform of that comb function. So it's just another comb function, but now the separations are 1 over delta x. So if this is 1/10 of a millimeter, this is 10 cycles per millimeter, this gap here. Okay. So now we can look at what does the Fourier transform of a sampled function look like. So here's our sampled function, g sub s of x. It's the continuous function multiplied by our comb function in the spatial domain. We'll take the Fourier transform of that function, and by the convolution theorem, the fact that a product in the spatial domain turns into a convolution in the Fourier domain, we see that we get the Fourier transform of little g of x, so we'll call it big G of kx, convolved with the Fourier transform of the comb function. And this is why we needed the Fourier transform of the comb function a few slides ago. So the Fourier transform of the comb function is here, right? And again, it's just a set of delta functions separated by 1 over x. And we're going to convolve the continuous true Fourier transform of the continuous little g of x with this comb function. So that convolution can move inside the sum because it's not dependent on n. And so we have the convolution of the continuous Fourier transform with delta x, and that sifts out the values of the continuous Fourier transform so that at each point kx in our Fourier transform of the sampled version of gs of x, at each point we get the value at that point of the pure continuous transform plus the values of that transform separated at units of 1 over delta x. So it's an infinite sum to get any value of the Fourier transform of the sampled version. And so what that means is that if we have a function here, which is the Fourier transform of our continuous function, this is the gkx, and this is our frequency components in that Fourier transform. When we look at the Fourier transform of the sampled version, it isn't just this one thing, it is a whole sequence of versions of this, right? and they are replicated at the sampling rate 1 over delta x. So you can see now how it's going to be important what we choose in terms of our sampling period or our sampling frequency, right? If we sample with a very small gap between sample points, so delta x is very small, then the separation between these replicants will get very large. It'll move away. And any one of those replicants then will be a more accurate representation of the true underlying Fourier transform GKX. In particular, if we know that our Fourier transform, our continuous Fourier transform of g of x, this GKX, is band limited, that means there are no higher frequencies than u or minus u, we can then set a criterion for how to sample little g of x such that when we take the Fourier transform of that sampled version, these replicants won't overlap at all. And so here's the continuous, value Fourier transform GKX. We have sampled such that the repeat of GKX, which is part of this, sampled version of the Fourier transform, if the frequencies come down to 0 before they overlap, then this representation of the Fourier transform is not corrupted at all by these replicants. And so we can actually write down a very simple criterion. We say, if this is our total bandwidth, let's say we want to sample out here to 2 cycles per millimeter, right, is our highest spatial frequency that we know is in our object. Then the total bandwidth I have to worry about is -2 to 2 cycles per millimeter or 4 cycles per millimeter. So if I set delta x to, or 1 over delta x to 4 cycles per millimeter, right, then I know that these will be separated broadly enough such that they're not going to overlap. And so this central one will be a good representation of the Fourier transform. That's called the Nyquist criterion. And it's quite simple. Our bandwidth, that we want to achieve has to be less than 1 over the sampling distance. Right? This can be called the sampling rate. 1 over delta x can be the sampling rate, say in cycles per millimeter, and this is the bandwidth in cycles per millimeter. If, on the other hand, we don't make that criterion, then what's going to happen is, if 1 over delta x is too small, the replicants move closer to our central copy here, and we start getting additions here. So our estimate of the Fourier transform is this plus this, which is going to be up here, and we'll get errors in the Fourier transform out at the edges. And then as this moves in closer and closer, eventually we'll see very low frequencies from this part of the first replicant blending in with these high frequencies. And we saw that happening with the spinning disk example. In 2 dimensions, it's basically the same thing. If this is our central set of spatial frequencies in the image on the Fourier space, we need to separate the replicants of the transform in the Fourier plane such that we don't get these overlaps. And if we don't do that, if we undersample in either delta y or we undersample with delta x, then these replicants will move in and we'll start getting corrupted estimates of the Fourier transform. Let's go back to our example that we showed above. You can see now that this sine wave is oversampled, actually. It's sampled very well. We have enough samples across the sine wave to know what the amplitude and phase of this thing is. And the question is, If this oscillation is going at 1 cycle per millimeter, let's ask the question, what sampling rate is the Nyquist frequency? Right? How would you need to sample if this thing is cycling at 1 full cycle per millimeter? What sampling rate do you need to hit the Nyquist frequency? And at this point, I hope that you can just answer that with common sense. Right? I know it's a little early maybe for common sense, but give it a shot. Give it a try. This is an example of what happens as you go from the adequately sampled condition towards the very undersampled condition. And we're going to move through the Nyquist sampling condition. This is a plane wave, and it has a kx of 1. Let's call it 1 cycle per millimeter. So every millimeter as I walk along the plane, I go through 1 cycle of a sine wave. My delta x for this diagram is 0.1. So that means I get 10 estimates of that sine wave for every millimeter. So I get a nice smooth function when I'm going along here. It looks like a sine wave. It looks very much like that function. If I drop my sampling rate, or I increase my sampling period, delta x, to 0.2, the function looks like this now. It's still a reasonable representation of a sine wave. I have a peak, a trough, and a peak, and they're occurring at the correct position, and everything looks okay. So one assumes I'm adequately sampled with a delta x of 0.2 and a kx of 1. So you can kind of guess where we're going here. Like, what is the Nyquist criterion going to be? Here's 0.3. Delta x is 0.3, or 3 cycles per millimeter is approximately my sampling rate. Right? Here's 0.4, so it's 2.5 cycles per millimeter. And here's delta x at 0.5. Recall my wavelength. I have 1 cycle per millimeter. Now I have 1 sample point every half millimeter, or 2 sample points per millimeter. Right? So now I have a peak and a trough, and a peak and a trough, and a peak and a trough. And that's perfectly sampling up and down, up and down, up and down. Right? And this, in fact, is where we hit the Nyquist criterion. So it's 1 cycle per millimeter. My sampling rate has to be 2 cycles per millimeter in order to represent that sine wave adequately. When I go below the Nyquist, I start seeing interesting patterns that show essentially lower frequencies aliasing back into the representation of this waveform until finally, when I'm at 0.9, right, that's very close to complete overlap of the samples, and I'll talk about that in a second. You see this very low frequency wave, right? The underlying signal that we're sampling here, remember, is this, right? However, it is showing up as this. And the reason is we're just poorly sampled, right? We're almost only sampling once per millimeter, right? What happens if we do sample it once per millimeter? Well, we would sample here, 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 here. So everything would be the same value. We would just get a constant, right? And that's complete overlap of those two versions of the Fourier transform in the sense that DC is now overlapping with our highest frequency, right? So in this example, we assume that the highest spatial frequency in the object, let's say, I use a different example while I was talking about it, but it is 1 cycle per millimeter. Therefore, the smallest spatial period is 1 millimeter, and the Nyquist theorem says you got to sample with twice that frequency, or 0.5 millimeters. So 2 samples per millimeter. Okay, and there it is.
Hi, Professor.
Hi there.
I wanted to ask, I want to make sure I phrase my question correctly,
Sure.
but so the
Okay, that just went to the next video, I think. Okay, so let's go back here. I'll just stop sharing. And does someone have a question at this point? There was one question that went by that I didn't have time, or I didn't thought we could do it together. Okay, so first, any questions right off the top there about sampling? Okay, so the cost of sampling at the right sampling rate these days isn't that high for the most part. I mean, digital sampling occurs now in many walks of life, and it's become cheaper and cheaper and cheaper. So you can usually do it in the time domain really cheaply. Spatial domain, especially if you have an X-ray detector, like an X-ray camera, putting more pixels in space is a way of increasing your sampling rate, so you could see higher frequencies, but that becomes expensive, and it also requires more photons such that each detector element gets enough counts to have good statistics. Let's see what we say. So one question that came on the chat was that do scanners use low-pass filters set with a cutoff frequency? And yes, they do. If you're receiving an MR signal from your scanner, and what happens is one side of the patient will be resonating at a higher frequency than the other side of the patient. And you can just set a filter. You can just run your signal through a filter in order to limit your field of view. That's a simple way of doing that kind of real-time filtering of the signal in MR. We'll see that in the phase encoding direction, it's a harder thing to filter things out, and they will alias back in. So you can certainly in one direction. Also with CT scanners, if you feel that there's objects well above the frequency that your grid is sampling with, those objects have the potential to alias signal back into your image and cause streaking and artifacts. And so you can, essentially filter the signal that you've measured to try and reduce those aliased high frequencies. Let's see what else we have here. So undersampled power graph waveform was actually just the waveform of the sampling frequency. Okay. Like we could go back to the video and look at the undersampled power graph, or go to that slide because I have it here. Let me share first the screen. Okay. This is 3. Okay. So the question, I think, was this one here. Was this what we're talking about? The undersampled power graph?
Yeah,
okay.
It was.
Okay, terrific. So we can go through this again. This is the underlying, this would be the sort of a radio frequency signal or some signal in time sampled at whatever this sampling rate is. And we can kind of figure that out by looking here. We're at 10 kilohertz, right, is the highest. So it's probably sampling about 20 kilohertz, right? And we get this Fourier transform of this signal. When we look at the same signal, but we drop the sampling rate by a factor of 8, right? Then the picture, when we plot those sample points, the picture actually looks different. The signal looks different. And when we take the Fourier transform of this, we get the power spectrum, but we get replicants of the power spectrum that are separated at that replication rate. So if they're separated every, 2 kilohertz, is that right? 2 kilohertz, 4, 6, I guess it's about, so we're going from 3 to 6. I don't know what that separation is. It's about, 2 kilohertz, maybe 3 kilohertz. So this part of the power spectrum here is identical to this. And these are the replicants that occur when you sample at a lower frequency. So really you only need
so I guess my question,
go ahead.
My question was, is your sampling frequency basically 3 kilohertz? And is that kind of like a practical way to see if you're undersampled? Because if you see the frequency of your sampling rate back in this Fourier transform, is that kind of like a double check on making sure that you're not undersampled?
Yeah, so the checking whether you're undersampled oftentimes is when you look at this and say, what is the separation of these and what is the power in the part of the spectrum where they're overlapping, right? So this now is not really an accurate representation of the underlying frequencies in this signal, because this is the accurate representation of what's going on out there, right? So it comes down, it looks about the same until you get here. These frequencies start adding in, and so you lose all of this information. So the question is, if you know ahead of time, you've got information out here, then you just need to upsample to make sure that you get that if this stuff is important. Sometimes when you're looking at this data, maybe all of the information you need is actually contained inside these frequencies. You can just filter the signal and get rid of these components out here that are unnecessary. Right, so.
Okay. And then in this case, if you look at the frequency spectrum and you're seeing that you have a signal that's like 10 kilohertz, would that mean that you want to sample at, 20,000 kilohertz?
Exactly, yeah. So if there is something out here that is important to the information that's being carried by this signal, then you certainly want to sample at twice this frequency in order to get this replicant over here, right? Because you're going to have a replicant still in it, but it'll be over here, and then the signal will come down here and it'll just start overlapping here. Hi, excuse me just for 1 second. I'll be right back. Okay, I'm back. We're going to do a few examples of a really simple function over here and looking at the Fourier transform, the digital Fourier transform and what it looks like after sampling it. Okay, so.
And then Elliot, I had one more question actually too.
Yeah, sure.
If you don't mind. So after we talked about the comb function, you gave that example where you like transferred it into the frequency domain, and then you had that repeating section. I don't know. I think it's like maybe like 10 or 15 slides down. The one where it was like the repeating hills basically, instead of the nice, there we go. Exactly. 35. Is that just because like a photodiode, for example, is not going to perfectly sample at one discrete value, but going to have kind of like a waveform? Or I'm trying to put that into perspective.
Oh, put this into perspective. Like what
Yeah.
this means?
Yeah, is this just like another like comb function that was convoluted with kind of like the more realistic like signal input that you're going to get from a photodiode or something?
Right. So this function here is in frequency space, and it represents all of the frequencies that are found in your signal. So if I have a picture, And that picture, you know, the objects in the picture have essentially a cutoff frequency, you know, so it's smoothed. Then I would have this bandwidth of spatial frequencies in that picture. And this, you know, goes off to infinity, right? And all this slide is saying is that if this is my actual spatial frequency content in my picture, when I do my sampling of that picture at a gap of delta x, right? And I represent that object in that picture with these discrete values separated by delta x, then what's going to happen is that I will see my underlying true bandwidth of the signal will be there in addition to these other sidebands, right? And when I look at the Fourier transform of the sampled object, this is the Fourier transform of the continuous object. This is the Fourier transform of the sampled object. I can reconstruct the object entirely if my bandwidth is such that, you know, 2 times this cutoff frequency is a separation here, and so these don't overlap. That's what this is saying. This is sort of just a placeholder function, right? For some potential spectrum.
And then what is that SAW, you know, waveform underneath it representing?
That's a great question. I forgot about the SAW function there. I don't really think it has a reason for existence. Tom, are you still on the line? Is this one of your slides? Do you remember what this?
Yeah, let me just see which slide are you, what's
so
the question?
Slide 35.
Yeah.
And why do we have this, looks like a phase function across the?
Yeah, it's just the linear phase. It's just showing the phase.
Okay. Okay.
Yeah. Or it's like it's probably the magnitude in the phase.
Yeah.
Yeah, because it's basically because the Fourier transform, it's for a real function, so it's got the Hermitian symmetry.
Right, right.
It's probably maybe it's the real and imaginary parts, probably what I'm showing.
Yeah. So sorry for the confusion, but I would just, I should have set up front. Just ignore the blue triangles down here, because you know, oftentimes the Fourier transform of your image, well, all the time, is a complex object, or is a complex function, as we'll take a look at. You're going to have a phase term, and so this would be the magnitude of the spatial frequencies in the Fourier transform in the phase. Okay, we'll look at that in a second. We're going to do some examples of discrete Fourier transforms with MATLAB. I know I went through one last week, but I think I'm going to take a step back, and we're just going to look at some simple arrays and what their Fourier transforms are, and you know, the complex nature of it. Okay. So let me see. Demetrius asks, can this low-pass filter be applied in frequency domain, or do you have to apply the filter before doing the FFT for CT? Well, once you're into the frequency domain and you've used an undersampled object to get there, you really have in that Fourier transform, you've got the aliasing, you've got the bad stuff in the overlapped regions. There is a region inside the Fourier domain in which, if there is a cutoff frequency, that those, you know, it will be accurate, right? But for example, here, you know, the frequencies in the Fourier transform of our object that's been undersampled out here are not going to be accurately represented in our Fourier transform, in our discrete Fourier transform, because it's got these replicants. However, right here, right, if this has gone down to 0 by that point and this has gone down to 0, then these components should be okay. So you have you can estimate lower frequencies in there. You can apply a filter at this point, you know, to reconstruct what the blurred or low frequency object would be, right? You get that accurately. But these once these have been mixed, it's hard to unmix them, right? You need to go back to the spatial domain and take more samples to separate these replicants in order to accurately estimate what those spatial frequencies are out here. Okay.
Professor, I have a question.
Yeah.
For sampling, when you're saying that you're like increasing the sampling rate, is that happening? Like, do you have to go back and rescan the patient, or do you go back to like the recorded signal and add more samples, discrete samples?
That's a really good question. It's a little confusing because we keep talking about sampling rate like it's a dial that you can just click on the scanner. And in magnetic resonance imaging, it turns out in some respects it is a dial you can click on the scanner. You can just sample at a higher rate with your electronics and also with your phase encoding steps. We'll see that in great detail. So in that way, you decide on how you're going to do your MRI acquisition based on the bandwidth of the object you want to look at. In CT, it's a little more complicated because you've got a grid already, right? That thing's been built at the factory. It has a sampling rate, and you're kind of stuck there, right? And the only way really to increase your sampling rate in CT a little bit is to take that sampling grid and essentially take one view and then shift the sampling grid by a half sample spacing and take another view, right? And that way you're kind of jittering between two views. It's going to take two looks, but that's it. Otherwise, the engineering decisions that were made in order to build the grid with that geometry kind of sets the sampling rate for the scanner, and to a certain extent sets the image resolution that you can achieve, right? On that.
Thank you.
Sure. Okay. Any other questions? So, you know, this is an example of the Fourier transform, the continuous Fourier transform, which is a rectangle function which goes to a sinc function, and we looked at this earlier. And everything looks wonderful when you look at the in you know, continuous form analytically, and you can do the Fourier transform analytically because it's this finite interval from a half to a half that can be solved with, you know, it has a result, and you get this output, which is a sinc function. Okay? So I thought, as an introduction also to MATLAB and how discrete Fourier transforms work in MATLAB, there are a few little subtle things that we should probably look at that you can carry with you. So I'm going to start up MATLAB or go back to MATLAB here. Okay. And can everybody see my screen okay? Is it looking good in terms of
Yes.
what's here? Okay, great. So this Fourier transform demo was put on the Canvas site after the last lecture when we went through a few examples of FT pairs. But what I've done is I've added something at the beginning, which is a sort of more basic version of the Fourier transform where we're going to look at the actual arrays in MATLAB and how things are represented. Recall when we constructed our function, we made a sampling rate and we made X in centimeters, and we placed points in, you know, in an array based at centimeters. Let's take a step back and do it even more simply than that. Okay, what we're going to do is we'll look at essentially a rectangle function. Even simpler than a rectangle function, it's just a constant and then it drops down to 0. And we'll have 512 points in an array, and we'll have a width to that function. We'll say 32 points in which the function is 1, and then it drops down to 0 after that. And that's done with this very efficient mask function, and then converted to floating point to give us our data. We'll look at that data, and then we'll look also at the Fourier transform, a very simple Fourier transform of that data, that array, okay? And you'll want to look at the help pages in MATLAB for the discrete Fourier transform, and it will give you a really detailed description of what's there. I think when I just went into YouTube or to Google, yeah, there we go, discrete Fourier transform in MATLAB. Okay, so this is what it does, right? So you have this array, X, right? And the thing about arrays in MATLAB is they're indexed from 1 out to whatever. So our array that I just showed you is 1 to 512. And inside that array, we're going to have a function, and then we're going to compute its Fourier transform, the discrete Fourier transform. This is the discrete version of the Fourier transform formula, where we just add up the product of the array with cosine and sine, and that's this function down here, right? And we have two variables. We have n that we're sampling, that we're summing over, okay? And we have k, which is our spatial frequency vector, right? So the Fourier transform at k0, like the 0 frequency, which means the constant value, when k is 0, that goes into the first element of our MATLAB array, because this goes to 1, right? And we take the sum from over the X array multiplied by this object as we're going across 0 to n minus 1, or in array coordinates 1 to n, okay? And that's how the Fourier transform is computed on the, inside MATLAB. And we'll take a look at some of the results here. Let's go back to MATLAB. Okay, so we're gonna reset everything. Okay, so let's take a look at this. So to begin with, here's our function. It's a rectangle function, essentially. From 1 out to 32, we have 1s. And then from 33 out to 512, we have 0s. And so I chose 512 because this is commonly the dimensions of a picture that you're going to look at. It's 512 by 512. In MR, oftentimes it's 256 squared, but once you get up to 7T images and these really high signals and noise images, they go up to 1K by 1K. So this is the easiest function we can look at, basically. And so what we do inside MATLAB is we have that function set up here. We've just plotted it. And we're going to take its Fourier transform, right? And to do that, it's just this simple function here. So the output of the Fourier transform, this array, is just the internal FFT of that array. And so when I look over at FT y rect here, it's 512, it has 512 elements, but it has 512 complex numbers as its output. Whereas our input function, y, had just real numbers, right? So when we go back, let's just do it again, take a look at it. So this is the output of the Fourier transform, but the real part of the Fourier transform. Okay, we're not going to look at the imaginary part just yet. And you can see it's a sinc function. It has this oscillation. What is its value at the first array element is 32, right? And the reason the value at the first array element, this is the k equals 0 value, the spatial frequency where k is set to 0. And why is it 32? It's because I have 32 ones along here and 512 minus 32 zeros along here. So this is when we set k to 0 in the DFT formula or in the FT formula, it just sets e to the minus j kn to 1, and we just add up all of the signal. It's an integral under our function, right? And that integral gives us 32 here. If we were to go back and let's set this, say, to 64, right? Just do it again, then we get a function that's twice as wide. It has 64 elements that are set to 1 out of the 512. And when we look at the Fourier transform of that, its peak is 64, right? Something else happened when we made it wider, is that the oscillations here became tighter, right? And so this rate of oscillation of these zero crossings in the real part becomes tighter. And we can see that specifically. Let's set this to 8 now, right? And run it again. So now I have a very narrow function, right? I have 8 elements in my array that are set to 1 and the rest are set to 0. And the function begins with a maximum value of 8, and then it has much broader oscillations before it gets to 512 in the Fourier domain, where it goes back to just below our maximum value over here, right? If I went to 513, it would have the same value here. So it repeats every 512 points, right? But it's important to know this is what is returned by MATLAB as the Fourier transform of that function, right? We can, let's go back and take a look at an illustrative example here. It's 32. Okay, so we're here. This is our Fourier transform. We can look at the first 64 points along here, so out to about here, and that's plotted down here. You can see that the first value is 32, which we just went through the reason why that is. The formula just returns the integral under the function. The next value is a little bit less than 32, right? So what does this value even mean? So what we're going to do now is in the Fourier transform formula, we replace the 0 and the k equals 0 with a k equals 1. And we look at that, at the result of that interval. Where's the, so it's here, right? We're going to replace this, instead of 0, it's going to be set to 1, right? And so we're you know, as we sum over this, it'll be e to the minus j 2 pi 1 times little n over big N, right? And so what's going to happen there is that this term, as we do this sum, it's going to go through one full cycle of a sine, of a cosine, right? So if we go back in here and say, well, what does this point represent? Let's go down. I was looking at this before, and we'll say, let's plot it on top of our function. So this is the cosine 2 pi times 1 over L, where L is our n in that formula. And if we look at that, we've now plotted that cosine, right? This is with k equal 1, and it's just one full cycle over the entire field of view of this object. The integral that gives us this value is the second element of this array. It's the k equal 1 point. The integral is the area under the orange curve from 0 out to 32, right? And so that, you know, we've just cut off a tiny little bit of that integral up here, and that gives us this second point, or this point right here, okay? And then as we, let's set that one to 2, and we'll take a look at that. CA to 2, plot CA. Now I have 2 full cycles of that cosine multiplied by my function, right? That gives us the value here, right? And it's smaller still because now I'm just integrating under this yellow curve here, right? To get my value of the Fourier transform at this point, right? Is that clear to everyone what's going on here? If we now set this thing to, I don't know, say 8 cycles, right? And we come out and we look at our 9.6, it's here, okay? So this is a k equals 8, get a value of 1, and that's this integral under here, right? Again, we haven't, we're getting closer to 0, but we haven't got there. As the frequency of this sine wave gets tighter and tighter with respect to this point. If we, let's go zoom in here. Let's see how this function, you know, is over this domain where the integral is actually going to give us something. It's the integral underneath this cosine here. So we're getting closer to 0 because the integral, the cosine itself crossed the 0 point here, and so we get a negative component of the integral here. And so that's how we create, you know, with the Fourier transform, this set of estimates. In the discrete Fourier transform, the continuous underlying function, which is, you know, best represented perhaps by this blue curve, is given back as these discrete values. Okay, these are the red dots that are actually in the array that is representing the Fourier transform of our object. We can trust this up to about here, right? And then it just is a mirror image around the point 256, and we go back out. And this pattern would repeat over and over again if we continue to plot that, right? And so that's an underlying representation of the fact that our sampling rate here is such that we can adequately represent frequencies out to here, out to half of the array length, because I need the sine wave, the cosine wave that produces a 1 up, 1 down, 1 up, 1 down is in fact 256 cycles over the full field of view, right? And so that's why we're seeing this function. It's accurate to here, and then it's just a replicant of itself going out to these higher frequencies. Okay, what else did I want to show here? Now, the other interesting part is this is the real part of the Fourier transform. The Fourier transform is a complex function, and so we can take a look at the sine, and let's plot. We're going to plot the imaginary part of the FT. Okay. So this yellow curve here is actually the imaginary component of the Fourier transform. And let me move my panel here. I'm going to zoom in manually on this. Okay, so here's the imaginary component. Recall that there's a cos theta term and an I sine theta term in the Fourier transform. This is the output of the integration after multiplying by the I sine k term in the Fourier transform. And you can see as we move to higher frequencies, so this is the sine wave over the sample here, we're going to get a different peak because as more of the function is moving in to overlap with our function here, we're going to see a higher a peak at the point where this is moved in to maximize that integral, right? these two should overlap at, let's put on the, so here at k equals 16, we will have a perfect, cosine replicant inside here that integrates to 0, and that gives us 0 in the real part. And in a similar way, we get a perfect sine replicant of one full sine phase in there that integrates to 0. And so we have our 0 crossing out here at k equals 16. And remember that k equals 16 means 16 full cycles over this array, right? That's what that number means. Okay? When you just look at this as the discrete Fourier transform of these matrices. So that's the underlying Fourier transform. There's a little bit of housekeeping in terms of the indices, because MATLAB has a 1 for its first index of an array, so that's always a problem. And then when you go to look at functions that are plotted as a position in space, what we do is we convert to these units where we have, each pixel is separated by, say, a millimeter or a tenth of a millimeter, and those are our estimates. And then we can look at the k-space as cycles per millimeter as well in those coordinates. Okay, so I'm going to stop there. I'll stay on the line if people have questions. And next week, we're going to get started on actually looking at how all this algebra and stuff comes together to describe how CT scans are reconstructed and how the data is first collected. Okay. Okay, we can just do office hours now, and I'll look at some of these questions we've got here. Can the slow pass filter be applied in frequency? Oh no, okay, I did that one. How come the waveform repeats? That's a very good question. I think I answered it, which is, when we look at our output here, let's just run it again, we'll get some output. And yes, the function, goes down, and it goes down as 1 over x as we're moving out here, 1 over x. And then it comes back up. This is, in fact, that replicant that we were seeing due to undersampling, right? If I essentially sampled this function with twice as many points, these replicants would get pushed apart twice as far, right? So we can do that. Let's go up here and we'll say, well, let's, instead of 512, let's do 1024. And we'll represent this as a rect with 64. So I've got basically twice as many sampling points here, right? Now, in absolute number units, 512 is here. So I've represented my sinc function out to 512 points. And then the replicant got pushed twice as far away. It's another 512 points over here, right? So with this discrete Fourier transform, because you always have a finite sampling interval, you will always have this interval, right, where the replicant occurs, and you just have to set your sampling rate in your function such that the frequencies you're interested in don't overlap, right, with the next replicant of the function. Let's go the other way. We could say, well, let's radically undersample it. Say if it's let's go back to 512, and we'll say our rectangle is 4 points, right? So now you've got a tiny little 4-point rectangle in here. I can zoom that up for you. Okay, so this is our function. And then here's the Fourier transform, the discrete Fourier transform of this 4-point rectangle. And you can see that our values don't get down anywhere close to 0, right? They're sort of, overlapping. So this is our first 0, even before our second zero crossing, they're overlapping, right? And so these two replicants are really interfering with each other at this spot. Let's do that even better. Let's go to 2. Let's see what happens with that. Okay, so now it's a total mess, right? So that's 2 points, and essentially it stops being a sinc function altogether. We lose all of the sidebands of the sinc function, and it becomes a essentially a sine wave with frequency 2, right? And or frequency 1, I should say, because it's at the first element here. So that's the only thing that survives. Okay.
So I'm sorry, could you repeat why it doesn't just stop, at the largest X, and why does the larger X values like have, a Y value? Like that's
okay. So why do we have values out here?
exactly, instead of just going to 0.
Right. Okay, so this is, let's look at it this way. So this is our function, whatever the heck it is, right? So it turns out it's a rectangle with width 64. Its continuous Fourier transform, if I had infinite sampling, right, would be a sinc function that decays away to 0 and just would keep going and keep decaying away, right? Because I am doing a discrete Fourier transform, just by the nature of the fact that I'm doing that I'm representing my function with discrete points and taking a Fourier transform with a finite number of points. Basically, I am in the sampled domain, right? So this is a sampled function now, and it has a delta X between sample points, right? Which is 1 over 512 or whatever. Yeah. And then, so what I'm going to see, and this is just the machinery of the Fourier transform. What they could do, if you want, is just to plot out to here and say that's all we can estimate is this frequency that is 256 cycles over the full field of view. It's the sine wave that has that frequency. The cosine wave that has that frequency is this one, 256. That sine wave, when you plot it, is just 1 point up, 1 point down, 1 point up, 1 point down, 1 point up, 1 point down, right? And that's the highest frequency we can represent in this finite array. And then we see the replicant here, the aliased replicant with its peak at 1 over the delta X, and our delta X here is 1 over 512, right? And so that's where it happens at 512. So it's sort of like,
okay, I think I get what you're saying. Yeah. So like as you get closer to that frequency, which is just the amount of data points, then you're still going to get some sort of like artifact there. And
right.
Okay.
So one of the things that is often done is that instead of plotting it this way, right, which is just the raw array, after that sum has been done, that formula sum, you can use a function called FFT shift, and it'll basically plot the data on this side, and this stuff it will put over here on this side. You still have the same width of frequencies represented, it just looks a bit better, right? And that's called FFT shift. And we can actually just run that. Where do we run the FT? Okay, instead of just FFT, let's call it FFT shift. Here, I think it should center those things. Who knows? Let's see what happens. Yeah. So what FFT shift does, it recognizes that that formula that is used for the digital Fourier transform gives you a peak at the k equals 0 point, which is the first matrix element array. And it says, no, that doesn't look too good. Let's put that point out here. And the higher frequencies go off in the wings, right? Now, this still, it just stops here. This still, if we kept going, it would just have another replicant over here. So it's sort of a convenience thing in many ways to plot it like this, because now you see your DC signal or your low frequencies are sort of at the center of your field of view of looking at the Fourier transform. So you'll see this done a lot, which is when the Fourier transform will get centered after the digital Fourier transform is taken, you'll recenter the Fourier transform to look at it like this. Right?
Okay.
Right, and so here's the, but these points, basically are all equal on one side to the next, right? So it's centered on this point and this point and this point are the same, this and this, this and this, this and this. So you don't have any new information here, right? It's okay. Let's take a look if there's anything else we want to look at here. So I would encourage you to take, I'll put this program up as well, and I would encourage you to take a look at just changing the width of the rectangle, the number of points the rectangle sample, perhaps move the rectangle, but I think we can do that down here. Once we get into looking at actual space, we can look at shifting things around and what occurs. But I did want to just address the fact that when you compute these discrete Fourier transforms, it's an array, and the output of the array is that one with the DC component or the k equals 0 component as the first matrix element. Right? And the highest frequency component is the essentially the middle of the output array. Right? When you're looking at, if we go take that FFT shift off, let's just do it. Yeah. Okay, so we can represent out to here. Okay. Any questions about that? Okay.
Professor, I have one more question.
Yeah, sure.
For the sine wave, is that like showing the sampling that you're doing of the rect function?
Which sine wave?
Like,
I'm sorry.
So like when you plot the rect function on the left window, is that
here?
that wave, the sine wave? Yeah, but the wave itself, the sine wave.
Yes, this guy.
The purple wave, yeah.
Mm-hmm.
Is that this showing the rect function? Because the rect function is what you're sampling.
Right. However, the purpose of showing the sine wave and the cosine, let's go back to just look at the cosine to make this point. The sine wave gets a little complicated. So if I look at a cosine function that has one cycle over my field of view, this is the function that inside the Fourier transform, I multiply my function by, and then I add up all of the components across the field of view, right? And so what I wanted to do was show what that function looked like when it was overlapped with our function that we're going to take the Fourier transform of.
Okay. So you're finding the component, like you're finding the cosine component of the rect function, or
correct.
Like,
the cosine component at this frequency, which is one cycle over the whole field of view. And
I see. Okay.
And that value is this value right here, right?
Yeah.
when you do that integral, when you look at the integral under the whole rect function, which is the cosine at 0 frequency, which is just 1, right? You just integrate the entire object. Then your value is 64 because I've got 64 ones here. When I then do my cosine with the k value in the Fourier transform equal to 1, I multiply by this, and then I sum up again, and I get the area underneath.
I see.
Okay?
Because the rec function is just like the sum of all these cosines, right?
Correct. And
All the different frequencies. Okay.
That's exactly right. And the question is, what amplitude do you use when you sum all of these together to create the rect function? This is a map of those amplitudes, the relative amplitudes, right?
Okay, I see. And it's just for the cosine function.
This is
You're
just
just
the
looking at
real
the cosine.
Yeah, this is just the real part.
Okay.
Okay. And so, in fact, if you looked at the magnitude, these things you'd have the sine part is in there as well, and you would see everything would be positive. So this is the coefficient that goes in front of the cosine term when you rebuild that signal using, cosine functions and sine functions. These are the coefficients that go in front of the cosine term.
I see. Okay. Thank you. Yeah.
Sure.
That's the one thing I was confused about.
Okay.
Yeah. Thank you.
Okay. And as this cosine wavelength gets shorter, i.e. I get more and more cycles across the field of view, I get more of that cosine occurring inside the rectangle. Now, the integral is always going to go down, right, as I'm moving in there, right? But I essentially, am able to derive these coefficients by multiplying those functions by the doing that integral.
That's because you get less of the higher frequency cosines within your rectangle, right?
That's right.
Within your rect function.
The amplitudes of the high frequencies goes down. And essentially you can think of it as like you need to make a big hump, and then you need to sort of make sharper and sharper edges. And those are done with the high frequency cosines, and they have lower amplitudes to be used.
I see. Okay. I think I understand now. Yeah,
okay,
thank you.
Great. Okay. Okay, any other questions? All right. Well, I'll post up this code, and you can, play around with it to get to know this is kind of like the native Fourier transform in an array or in a matrix. And then when we come down here, we start looking at making a coordinate system that is in centimeters and a spatial frequency coordinate system that cycles per centimeter. And we start using these FFT shift functions to look at the transform or move the transform to the center of the field of view. And I think all that should still work. Let me set it here. But if not, the one online does work for sure, right? One that's already been posted up. Okay, make a sine wave. Okay, so here's a sine wave, and this is its Fourier transform, right? And we've got spatial position x in centimeters, spatial frequency k in cycles per centimeter. And all of those scalings are done here to convert the actual position in the matrix, in the array, into a value of spatial frequency as opposed to just a number, right? And Again, you can look at changing these things, frequency and cycles per unit length. So if we did, you know, 2, change that to 2 cycles per unit length, right? So we get a much higher spatial frequency, and the Fourier transform components move out to higher frequency units. Right?
It's only one frequency, right?
This is one frequency, exactly. All I've got is 1 here. You can, if you want, you could make, you know, a sum. You could, instead of just having a sine wave, you could, you know, make whatever you want here, which is a combination of different sine waves, and see if the Fourier transform pulls out those frequencies accurately.
Okay.
I mean, a way to do that would be, let's say we just went plus, you know, sine of all of this, but we're just going to put a 2. Like that. I think let's put a 3 here. Say 3.